Welcome to section 1.3 Propositional Equivalences. This is Dr. Gilbert, Eyabi. Math 160 Discrete Methods, Anderson University, and we are still using the text Discrete Mathematics and Its Application by Kenneth H. Rosen. Section Objectives. We would look at tautologies, contradictions, and contingencies. Then we would move down to logical equivalence and look at some important logical equivalences and how to show logical equivalences. And then we would skip right down to propositional satisfiability. Now let's go ahead and start. Definition: tautologies, contradictions, and contingencies. A tautology is a proposition which is always true. For example, P or not P is always true. He ate a slice of pizza or he did not eat a slice of pizza. That is always true. A contradiction, on the other hand, is a proposition which is always false. For example, P and not P. He ate a slice of pizza and he did not eat a slice of pizza. It's a problem. Contradiction is always false. And thirdly, we have a contingency. A contingency is a proposition which is neither a tautology nor a contradiction. It's just a proposition. It could be true or false depending on more information. So for example, P, he played soccer this morning. We need more information before we can conclude whether it's T or F. Now let's look at the truth tables for contradictions and tautologies. So we have P and we have not P. Again, just one proposition, so two truth values on the column. And P or not P, we end up with TT, all true, so that means a tautology. P and not P, we have FF, and that means a contradiction. Okay, now recall truth tables. We've done this before. Or is true if any one of them is true. It's only false if both are false. And we don't have that situation, so it's all true. And on the other hand, it's only true if both are true, otherwise false. And we do not have that situation, so it's all false. So here we have a tautology, and here we have a contradiction, all true and all false. Now let's move on to the next objective in section 1.3, logical equivalence. How do we prove or how do we show that two propositions are logically equivalent? Well, two compound propositions P and Q are logically equivalent if the biconditional P if and only if Q is a tautology. We can also represent that with P if and only if Q, or P is equivalent to Q where P and Q are compound propositions. Additionally, we can also say that two compound propositions P and Q are equivalent if and only if the columns in a truth table given their truth values agree. So, two compound propositions are equivalent if and only if their respective columns agree. So there are two ways to prove that two compound propositions are logically equivalent. Number one, we can show that P if and only if Q is a tautology. Number two, we can show that the two columns that give the truth values of these propositions agree. Let's go ahead and verify that for these two propositions right here. One is not P or Q. P implies Q. We claim that P implies Q is logically equivalent to not P or Q. By the way, we establish logical equivalence. We can always replace P implies Q with not P or Q and vice versa. So that's why we are interested in logical equivalence, because if I have P implies Q, I can simply write it as not P or Q and it would still be the exact same thing. So let's verify that. We have two propositions, so we're looking at 2 to the 2, which is 4 truth values. Here we are. That's P, that's Q. We have not P, and then we go with this first guy right here, the first compound proposition, not P or Q. Not P or Q gives us this column, and we move on to P implies Q. It gives us this column right here, and we observe that this column, not P or Q, the other column, P implies Q, the truth values agree. So we can stop right here and conclude that these two compound propositions are equivalent. But we said something about tautologies. So we could also do not P or Q if and only if P implies Q. And recall that if and only if is true, if and only if both truth values are the same. So T and T is T, F and F is T, T and T is T, T and T is T, all true. That is a tautology. So if you did not want to conclude using the fact that these truth values agree, you could just go down here and look at the last column and say that because we have a tautology, the compound proposition not P or Q is logically equivalent to the compound proposition P implies Q. So that is one way of verifying that two compound propositions are logically equivalent. And I would expect you to use that very often. I'll also show you some other ways of verifying that two compound propositions are logically equivalent without using a truth table. Augustus de Morgan, 1806 to 1871, gave us what is known as De Morgan's laws. It's very popular. You see that in set theory, in logic, almost everywhere we have De Morgan's laws. It claims, number one, that not P and Q is equivalent to not P or not Q. The and changes to or, and both propositions are negated. The second one, the or changes to and both propositions are negated. So prove that this compound proposition is logically equivalent to this, and this compound proposition is also logically equivalent to this. We're going to do one of them, and you would do the other one on your own. Let's look at not P or Q. De Morgan claims that not P or Q is logically equivalent to not P and not Q. Well, if you do your truth table, we have P, we have Q, we have not P, we have not Q. And because we are going to deal with not of all of this, so we start off with P or Q and then negate that. That gives us F, 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 T. And then we look at not P and not Q. So here are the two columns we're interested in. Again, and is only true if both truth values are T. So FF is an F, FT is an F, TF is an F, TT is an F. Both columns are the same. The truth values agree. So we can conclude that these two compound propositions are logically equivalent. Or we can add a final column, which is not P or Q if and only if not P and not Q, and observe that we end up with a tautology again. This is true if and only if both truth values are T. So we have F if and only if F is T, F if and only if F is T, F if and only if F is T, T if and only if T is T. So we have a tautology, and therefore we can conclude that these two propositions are logically equivalent. So I think as far as truth tables are concerned, we know how to verify that two compound propositions are logically equivalent. Is there any other way to verify logical equivalence without using truth tables? Before we get there, let's go ahead and give you some very important, useful logical equivalences. We call them key logical equivalences. And yes, you are welcome to use some of these when you're proving logical equivalences, because these are already done, they've been proven. And the whole, the identity laws, P and T, it doesn't matter what P is, P and T is always equivalent to P. P or F is equivalent to P, and we have the domination laws, we have the idempotent laws, we have double negation laws, not P, it's P, and you can verify all of this. You can actually construct truth tables and verify each of these. I'm not going to ask you in a test to state the identity laws, or the domination laws, or the idempotent laws. But I do expect you to know these laws and to be able to use them and apply them in solving problems. We will see an example as we move on. Some more logical equivalences: commutative laws, associative laws, distributive laws, absorption laws. Verify this. I'm going to ask you to do some of this in class, but I expect you to verify them yourself even before you get to class. For example, the distributive laws. You want to verify that P or Q and R is logically equivalent to P or Q and P or R, and so on and so forth. And even more. These ones are actually very interesting, and I need you to remember at least a couple of them. For example, you should be able to know that P implies Q is logically equivalent to not P or Q. We already proved this using truth tables. And as a matter of fact, P implies Q is also logically equivalent to not Q implies not P. Remember our contrapositive thing? So there are so many of them, you just need to go through this. I might give you some of these tables in a test for you to use when you're proving logical equivalences. But I need you to know how to at least use these known key logical equivalences. Okay, let's look at constructing new logical equivalences. We can show that two expressions are logically equivalent by developing a series of logically equivalent statements. Remember, I did say that you can verify the logical equivalence of two compound propositions by using a truth table, or you could do that in a different way. And this is the different way. To prove that A is logically equivalent to B, we would produce a series of logical equivalences beginning with A and ending with B. That's going to be fun. Okay, now as we proceed, I want you to keep in mind that whenever a proposition represented by a propositional variable, for example, P implies Q, occurs in the equivalences that we've listed above, all those many key logical equivalences, each of those propositional variables can be replaced by an arbitrarily complex compound proposition. So when you see P implies Q, it could be a huge complex compound proposition implies another complex compound proposition. All you have to do is apply the key logical equivalences and go from A to B without breaking your leg, without making an error. Let's try a few of those. Example 1. Show that not P or parentheses not P and Q is logically equivalent to not P and not Q. Again, you can use truth tables to get this done, but here we expect you to prove that this compound proposition is logically equivalent to the other one without using truth tables. Use a series of logical equivalences. So let's start. So we start with the left-hand side right here. It's a lot easier to break down a house than to build one. So we start off with this that looks really huge and break it down to not P and not Q. So we start right here. And what is it that we see? Oh, wait a minute. De Morgan's laws. If I distribute my negation sign, P gets negated, the or becomes and all of this gets negated. And then I can take the negation further in, applying De Morgan's again, and so on and so forth. So we apply De Morgan first, and that gives us not P and not into not P and Q. That's good. We leave the left component all by itself. The and still stays. I distribute my negation again using De Morgan's. The first component gets negated, the and changes to or, and the second component also gets negated. So that gives us not P or not Q. But wait a minute, not P is P, one of the key logical equivalences. So that gives us not P and right here, P or not Q. So what do we do from here? Oh, wait a minute, the distributive laws. We can distribute these and it gives us not P and P or not P and not Q. Wow, that's beautiful. Wait a minute. What else? Oh, not P and P is always false. That's a contradiction. So that is F or not P and not Q. But F or something gives us what? Let's go back and look at it. F or a proposition is the proposition. It doesn't matter how complex the proposition is. That compound proposition or false is always the proposition. So let's go back to our problem. All of this or that, and you could see that if we really want to make it look exactly like the key logical equivalence we just looked at, we can use our commutative law. to flip this around, and then we apply that key logical equivalence, and we end up with not P and not Q, which is exactly what we are trying to prove, and we are done. So if you are given a problem in this class and you're asked to verify that two compound propositions are logically equivalent, you can do that either by using truth tables, or you can do that using a series of logical equivalences. But of course, if I specify that use truth tables, you have to use truth tables. And if I specify that do not use truth tables, instead use a series of logical equivalences, then I expect you to do it exactly like this. I think we need one more example. Example 2. Prove that P and Q implies P or Q is a tautology. Again, you could use truth tables, except you are asked precisely not to do that. Or you could use a series of logical equivalences. In this case, we are using a series of logical equivalences. So what are you actually asked to prove? To prove that this is a tautology, you are basically proving that the very last column would give you all true. That is if you use truth tables. But let's go ahead and look at a series of logical equivalences. Solution. P and Q implies P or Q. So we get stuck right here. How do we proceed? Then we remember that P implies Q is logically equivalent to not P or Q. In this case, that is your P. All of this your P and all that is a Q. So all of this implies all of that is logically equivalent to not the first component or the second component. Now, De Morgan comes in. De Morgan goes in. We have not P or not Q or P or Q. That's very good. And from here, all we have is or. We can move things around by associativity. We can move things around by commutativity. We can do just whatever we want to do because it's all or. So we move this P around. We end up with not P or not Q or Q. But not P or P is true. Remember? Not Q or Q is true. Both are tautologies. So we end up with T or T. And T or T is always true. What have we done? We've successfully shown that P and Q implies P or Q is a tautology. It's always true. This whole concept introduces you very slowly to the concept of proofs. We would use this same idea to prove a couple of things in set theory and even beyond that. Now let's talk about propositional satisfiability. A compound proposition is satisfiable if there is an assignment of truth values to its variable that make it true. So if I give you a compound proposition and ask you whether it is satisfiable or not, what I'm actually asking is it possible that there is an assignment of truth values to the variables in the compound proposition that would make the compound proposition true? When no such assignment exists, the compound proposition is unsatisfiable. So a compound proposition is unsatisfiable if and only if its negation is a tautology. Interesting. So if I give you a compound proposition and ask you to prove that it is unsatisfiable, well, you could check all possible combinations of truth values and show that there is no possible assignment of truth values to its variables that will make it true. Or you could just come up with a truth table and show that the negation of that statement is a tautology. That's beautiful. Let's look at a few examples. Example 1. Determine the satisfiability of the following compound propositions. The first one right here, is it satisfiable or not? By observation, if we assign T to all three, P, Q, R, then we end up with the compound proposition being true. So it is satisfiable. The second one, again, if we assign T to P and F to Q, then this compound proposition ends up being true. So it is satisfiable. What about the last one? Well, it is not satisfiable. And it is pretty tough to verify that because you have to come up with all possible combination of truth values and show that no assignment of truth values to the propositional variables would lead to the proposition being true. or we construct a truth table and show that the negation of this entire compound proposition gives us a tautology. That should probably give you an idea. If you are verifying the satisfiability of certain compound propositions and it's a little bit difficult to come up with a conclusion, you may just want to do a truth table and check the negation of the compound proposition. If it's a tautology, then we're done. Now let me end with some notation. Observe that this is just or j from 1 to n pj. What this simply means is p1 or p2 or pn. Remember, j goes from 1 to n. J is just a dummy variable. Same thing for and. And j from 1 to n pj just means p1 and p2 and 3 and pn. To make that even easier, let's use just two propositional variables. P1 or P2 would be or I from 1 to 2. Let's make that even easier. Why don't we use just two propositional variables, P1 and P2? P1 or P2 would just be, you have your or, I from 1 to 2, pi. I is just a dummy variable. P1 and P2 would just be and, I from 1 to 2, pi. So, P1 or P2 or P3 or P4, what would that be? It would be or, I from 1 to 4, pi. P1 and P2 and P3 and P4 would just be and, I from 1 to 4, pi. We would use this concept in proofs. But that brings us to the end of section 1.3, Propositional Equivalences. Thank you, and I will see you in the next lecture. Bye-bye.